All right. Hello, class. Welcome back. So today we are going to be talking about, it's the last lecture in our section on orbital mechanics. The next lecture we'll be getting into attitude dynamics, so spacecraft motion, and how the satellites move around and position themselves. But in this lecture, we're going to be talking about sort of a combination of all the things that we've talked about so far and its application to interplanetary space travel. So how to get from we've talked a lot about orbits of the Earth and orbits of anything really, single two-body problem. But in this lecture, we're gonna try and expand our horizons a little bit and figure out what the application of what we've learned is to traveling to other planets. And I include the moon in that sort of category. Now, I want to say right off the bat that we're going to do something a little bit different in this lecture to try and make things, I guess the word is digestible. For the audience, and so I'm gonna break this lecture down into 3 sub lectures. So let's see if I've got to so we're gonna talk about. I'm gonna have 3 different videos, and I'm gonna record them all at the same time, but there'll be 3 of them. And the idea is just to make it a little bit more organized. So the first lecture, the first sub-lecture will be on this one, on the sphere of influence, proper definition of the sphere of influence. You may think you know what it is, but it's a little bit more complicated than you probably think. And we'll throw in, actually, I didn't talk about it here, but we'll throw in some stuff about the orbit of the moon as well. So then I'll take a quick break, and I'll come back and I'll talk about the second, which is probably the biggest part of the lecture, which is mission planning. So how to leave the sphere of influence of the Earth, transit through the sphere of influence of the Sun. Here's the Sun, here's the Earth, here's your destination planet, Mars, say. And there's the Earth. So I'll talk about leaving the sphere of influence of the Earth, transiting the sphere of influence of the Sun, and what happens at arrival at the sphere of influence of the other planet. So in this case, it's Mars. Although actually, the example which I'll be working through in the second part of the lecture is actually a transit to Venus. So shouldn't actually say that's Venus. Well, mention Mars and transits to the moon and stuff like that, but we'll be focusing on that Venus mission plan, as is in Prussing, right? We'll be following the Prussing and Conway, example that they use. And then the third and relatively short lecture, so I'll call this lecture 14.1. This is 14.2 and 14.3. And the last one will be on gravity assist maneuvers. And so how to use the gravity of planets through flybys to boost your velocity in the heliocentric coordinate system. So to give an absolute delta V boost to your spacecraft. Okay. So that's the organization we're going to be going through. I'll get into the details here later on. I don't want to overwhelm you right now. Right. So just to give some idea of what are the pieces of a interplanetary mission, right? So what are the essential features of any mission planning problem? Well, there's several obvious ones, and Again, I don't. There's not much new in the way of fundamental mathematics or orbital mechanics that we're going to be going over today. It's more application of those from a sort of a practical standpoint, how to put all the pieces together, right? And so there's nothing here in this these points which is actually new that you'll learn, but putting all the pieces together and getting your mission organized is what we'll be focusing on. Right, so there's there's various pieces. Again, we've sort of mentioned them all at some point or another, but I'll mention them again. The first is, of course, launch, right? Establishment of a parking orbit. So you need a delta V of about 10 for that launch, right? An establishment in a parking orbit, right? Get a little delta V boost right there, right? You hang out in your parking orbit until an appropriate time is reached, at which you do a delta V burn to escape. Oops, wrong direction. Maybe I'll make it a new color. Do a delta V burn to escape. So you reach escape velocity. And that means essentially that you'll leave the sphere of influence of the Earth, right? So that's the part where you're leaving the sphere of influence of the Earth. And then once you've left the sphere of the influence of the Earth, well, then things change a little bit because your coordinate system changes. So here's the sun, right? And it turns out, right, the Earth is rotating about the sun. Who knew? And so once you leave the sphere of influence of the Earth, you have some excess velocity. And so your velocity gets added to the velocity of the Earth, right? And then you transit in some path in the heliocentric frame until you arrive at your destination. So there's a Hohmann transfer maybe here in the middle. Right. And then you arrive at your destination, and then the steps are reversed. And that's sort of interesting because we haven't really talked about reversing these steps, right? So you say, make a little connecting line here. And we arrive at, say, the sphere of influence of, let's say, Mars here. Here's Mars. Right? And then we're on this hyperbolic orbit, right, about Mars. Right, and so we want to get the parameters of that hyperbolic orbit just right, so that we end up close to Mars here at periaps, and so we need something called a targeting radius, right? And then when we get to Mars, well, there's a couple things we can do. We can have a capture maneuver. It's usually a retrograde burn. So there can be aerobraking involved, a delta V maneuver. And that can either put us in a capture orbit, so a very elliptic orbit, or it can put us in a parking orbit around Mars. And then at some point we need to, we can either circularize or we can just fly by. And then if we want to do more than just circularize, we can actually land. We can get the delta V for landing as well. Again, that's a retrograde. So it's sort of the reverse of the launch at arrival, right? Instead of escaping out of the sphere of influence, we inject ourselves into the sphere of influence. Instead of establishing a parking orbit, we get out of a parking orbit. That kind of thing. So, as I said, right, there's really the difference is that before we were talking about a two-body problem, right? Talking about this two-body problem, where we have a single thing we're orbiting, which is very big, and we've got our spacecraft, which is small. Right, and so that was a fairly restrictive case. And now we're going to be talking about, well, there's at least 4 bodies involved in this case. What are the 4 bodies? Right. Well, there's the sun, Right? There's one body. There's the Earth, which is two bodies. There's Mars or Venus, or the planet we're going to, which is a third body. And of course, don't forget, there's us. We are a body as well, right? So let's not forget us. There's my spaceship. All right. So actually, 4 bodies are involved here as opposed to just 2. And so that's like a relatively complicated problem. So I say 3 bodies. In fact, actually, right, we should really be saying 4 bodies, right? If we're thinking about this right. So fortunately, unfortunately, of course, solving a 4-body problem, like just the dynamics of that, are very complicated. So it's just going to be beyond us to actually calculate what those, the acceleration and integrate that. And it's not non-Keplerian, very non-Keplerian. Fortunately, however, we have a simplification that allows us to compute transfers. And that's the sphere of influence model. Right? So this is what we're going to be talking about in this first part of lecture 14.1, the sphere of influence model. So what is a sphere of influence model? Well, it's not terribly complicated. Basically, it says that usually, right, and there are exceptions to this, like binary stars and so forth. Usually, one force, one central body, is in charge. Someone's in charge at all times. And of course, what we're going to answer in this lecture is who's in charge. What do we mean by in charge? Well, that's an interesting question. What we mean by that is, I'll just highlight in charge. What I mean by in charge here in this case is I mean that the motion about that body looks like, is approximately like two-body motion. That is, it looks Keplerian. So two-body motion. As in elliptic. We are these orbits, Kepler's 3 laws apply. So we're going to be establishing conditions on which the motion looks like Keplerian elliptic motion, and then we'll hope that the transition between those points is relatively short, right? So, for example, like if we look at this picture here, right? This illustrates the sphere of influence of the sun versus the planets, right? Let's see, what do we got here? I think this is Mercury. This is Venus. That's Earth. That's Mars. Right? And so who's in charge? Well, the point is when you're close to, say, Mars, I'm just saying that, using Mars as an example because it's like the farthest out and it's easiest to draw, right? It turns out if you are within the sphere of influence of Mars, the motion about Mars looks roughly Keplerian, looks roughly elliptic or hyperbolic, depending on how much energy you have. Now, that the region where that applies is not very big, right? So if I use my little highlight tool, right? It's just within this green little band right here about Mars. So not very big in the grand scheme of things of the solar system, but accurate out to a few 100,000 kilometers, right? So this is these widths here are, right, a few 100,000 kilometers. I think, what is the sphere of influence of Mars? I'd have to look it up. The sphere of influence of the Earth is about 850,000 kilometers, I believe. And so this one's, right, this width is 850K. K megameters, if you will. I forget the one about Mars. I'm guessing Mars is smaller, so I would guess it's around maybe 400,000. Right. So anyway, not big in sort of solar system type scales, but when you're close, it looks sort of like it looks big, I guess. That's the point. So we have this idea of a patched conic, right? Conics referring to, right, that refers to the ellipses. Or, of course, the hyperbolas. Right? So patched conics. And that means when you're in this band right here, you are in an ellipse around Mars, or a hyperbola on Mars, a conic around Mars. And when you leave it, you're in a conic around, well, not Mars. You're not close enough to be Earth. So what you're actually in an orbit around is the Sun. And that orbit is also conical, right? It's typically elliptic, but it could be hyperbolic, right? So this little section here, this little red section between the bands is conic about the Sun. Right? And yes, there is a transition period, right? So there's a transition period where the elliptic motion about one of those two bodies doesn't look very elliptic, right? Patch points, we call them, right? There's a patch point. There's a patch point. And there's two patch points here, of course. One when you're entering and one when you're leaving. And I guess I could draw those for all of them. And yeah, so I don't think we don't even draw the sphere of influence of Mercury here, I guess, because it's fairly small. Okay. And so our first goal here is going to be talking about where those patch points are. So we can propagate out. We can use our elliptic-like motion within that sphere of influence model. And then, of course, we have to transition. We hope we transition relatively quickly, but of course, it's could be some corrections that need to happen. Right. And so, right, as I said, in this lecture, we talk about where those patch points are, and what they mean, right, and how to find them. Right. So basically, the patch points occur when the Keplerian motion fails, right? The conic approximation fails. Right? And when does that happen? Well, remember in the last lecture we talked about disturbances to the orbit. Right? And those disturbances were approximated as just changes in our orbital elements, assuming that the mean motion, or the motion of the spacecraft is a conic or is elliptical, right? What we're going to be taught, so we're going to be using, well, we're not going to be using the equations very much, but we use that same logic to find the point at which the disturbance becomes too large. When does that disturbance become so large that the elliptic or the conic approximation of the orbit just fails entirely? Right? And then, of course, picks up when we get to the other body. And basically, the criterion for a patch point, the criterion for a patch point is when does the motion around one body look more conic than the other? So which motion looks more conic, right? So the spacecraft around the sun, for example, or the spacecraft about the Earth. Right. So that's the sphere of influence. That's what the sphere of influence means. Okay. So who's in charge, right? So of course, there's an obvious definition for the sphere of influence, an obvious way of defining it, which would be so say you're the moon, for example. So whose sphere of influence is the moon in? Well, the obvious answer to that would be that the moon is in the sphere of influence of whoever exerts the larger force. Right? That makes sense, right? Larger forces means larger accelerations. So the force on the moon due to the sun, right, is larger, say, than the force on the moon due to the Earth. So therefore, the acceleration of the moon due to the sun is going to be larger and more disturbing than that of the Earth. Right? That's a sort of a intuitive sense of the sphere of influence, but it's completely wrong. So don't use that. No. And why is that? Well, that's what we're going to be trying to explain, mostly through mathematics, but partly through intuition. And well, first of all, you can see intuitively that it's wrong because the force on the moon due to the sun is larger than the force on the moon due to the Earth. Right? Force moon sun is much, much greater than the force of the moon on the moon due to the Earth. Right? So that would imply, if we use that definition, that the moon is in the orbit is orbiting the sun, which of course seems silly. But it's not that silly. Does the moon orbit the sun? So let's take a moment and think about that for a second. Does the moon orbit the sun? Well, I think we can agree that the Earth orbits the sun. Yes, I think we're safe with that. But does the moon? I'll put a little exclamation there. Definitely, we're okay with that. But does the moon? Well, if I look at this, right, I mean, the moon is going around the sun, around the Earth. True. But it kind of looks like the moon also goes around. I mean, the moon goes around the Earth, and the Earth goes around the sun. So technically, the moon is also going around the sun, right? So, what does that mean? Right, so the moon is going around. It happens to be orbiting Earth while it does so, right? So technically, the moon is orbiting the sun. It just has this sort of perturbed, right, motion. Right? It is going around the sun. So that's an interesting observation, right? And that gets to the heart of this question of, why this model of the sphere of influence is wrong. Why the maximum force model is wrong. It's wrong, of course, because pretty much everything's orbiting the sun, right? I mean, everything's orbiting the sun. But it doesn't tell us much, right? It doesn't tell us much about what's going on. So the sphere of influence is really designed, the model is designed to let us do this patched conic approximation. And so, well, the moon, or motion of the moon around the sun, right, if we're going to model that with a patched conic, right, that would just be the Earth, right? And so if we wanted to actually model the motion of the moon about the sun, right, we could just take the position of the Earth, which we know pretty well, and then we could add the vector of the moon with respect to the sun, to the Earth, right, and get this, right? So this plus this will get us this, right? And so since we already know this, finding this is not very helpful, right? And so what we really want to focus on is this one. Right, the motion of the Earth, of the moon relative to the Earth, right? And the reason is that, of course, imagine that the Earth exerted no force on the moon at all, right? Then the path of the moon and the path of the Earth would look almost identical, right? They'd be, they're a little bit off on their orbits, but they'd be almost identical, right? And so it's that identicality, right? That the lack of sort of valid information that you're getting from this, the motion of the sun relative to the moon versus the moon relative to the sun versus the Earth relative to the sun, that defines what piece of information is important, which patched conic we should be looking at. So that's me trying to give you the intuition behind what's going on. So let's get to the mathematics a little bit more. So again, right? If we're going to continue our, so here's the picture, right? Here's the sun. Here's the Earth, right? Oops. Here's the Earth. And why not? Let's make this the moon. It says vehicle here, but let's make it the moon. So V is for vehicle, or vehicle. Right. So we've got these this sort of triangle here, and intuitively we see that we know that this object here, which is probably not the moon because it's much farther from the Earth than the sun, right? We intuitively know that this is going to be in the sphere of influence of the sun. So the vectors here are, right, we've got the motion of the planet with respect to the sun, motion of the sun with respect to the planet, which is also turns out to be important. There is a barycenter here. It's actually within the radius of the sun, but okay, let's ignore that. And the motion of the vehicle with respect to the sun, and the motion of the vehicle with respect to the planet. Right, so lots of things going on here. So because this particular vehicle happens to be closer to the sun here than the Earth, we're going to start by analyzing the ellipse, or the Keplerian motion of the vehicle with respect to the sun. So vehicle with respect to the sun. So that's this, basically. That's the acceleration. Pardon myself, spelling. So that's the acceleration. And if we were to scratch off all this bit, the disturbing forces, right, then the equations of motion would just be this one, if there were no planet involved at all. Right, we would just move, this would be negative mu over r squared onto the right-hand side, and this is the Keplerian motion. So that's the conical approximation. So now we have to look at, right, what's the disturbance to the Keplerian approximation. Okay. So this is the Keplerian term, right? And this is the non-Keplerian term. Non-Kepler. And so what we want to do is we want to figure out how much these terms affect this, right? How much not like a conic this is going to make this look like. So let's look at the conical motion, right? If you will, change our color here. Conical motion, right? And these are the disturbances that we talked about in the last lecture. So the extent to which our motion around the sun looks conical, or Keplerian, right, is going to be determined by the extent to which these can throw off our orbital elements. These terms right here. And the extent to which they can throw off our orbital elements is determined by their relative magnitude with respect to this. So specifically, what is the ratio of the disturbance divided by the ratio of the sort of a conical part of the Keplerian part of the motion, right? So that's what we're going to be looking at. So let's look at these bits. What are these bits? Well, we know what this bit is. This is the relative sun-moon vector, or sun-vehicle vector, right? And divided by the distance between the sun and the vehicle, right? We're pretty familiar with that. All right, so what are these terms, right? Well, so that's the effect of the sun on the object. This is the effect, right? This is what you expect to see. This is the effect of the planet, so the acceleration of the vehicle due to the planet, right? So this term, let's highlight there, right, gets drawn down to there, right? So that's really the extent to which, right, this is going to rotate, move back and forth, right? That kind of acceleration. The next term, however, is a little bit more interesting, right? And you'd expect it. I don't know what you'd expect it to be, but this is what it is, right? That's the acceleration of the sun due to the planet, right? So technically, right, this point, this term here accelerates a little bit, right? So this term actually, there is some small motion here, right? The planet does exert some relatively small motion, acceleration on the sun. It's minor, and of course, if we're talking about other two-body problems like, say, Earth/Moon, right? So if this was a moon, for example, and this was the Earth, right? We were trying to figure out whose sphere of influence we were in there. Then obviously the Earth does have a significant contribution to the motion of the moon. So just FYI. But anyway, so this is the effect of the Earth on this vector here. And that's important, right? Because if this, right, this vector goes all the way over here, right, that's going to change the length of this vector, right? So this does act as a disturbance to the relative position of the vehicle with respect to the sun. Right? So those are the two contributions here to the disturbances: the acceleration of the vehicle, right, due to the Earth, and the acceleration of the sun also due to the Earth. Now, as I mentioned, of course, if we were talking about like the sun, whose influence the moon is in, right? If we're looking at the question of whose sphere of influence is moon in, right? Then if we look at this, right, then the acceleration of the sun due to the Earth is approximately 0. Right, so that's approximately 0. And so no matter what this term is, the acceleration of the moon, right, it'll be greater than the acceleration of the sun. And so when we pop these things into the equation on the previous slide, so if we just divide this acceleration, the disturbing acceleration due to divided by the Keplerian, sort of the nominal terms, right, then well, this term drops out, and so we go to the previous slide. Right, we can just ignore that term. Oops, I think I went the wrong way. So we can just ignore that term there, and so we can ignore that term there. And so if we just divide this by this, right? Well, what do we get? The g's drop out. We get the MP divided by MS, and then we have a 1 over term here. Let's like just drop the magnitudes here. We'll take the magnitude of these disturbances, and then we have R sun vehicle squared divided by R planet vehicle squared. Right. So that's what we see here. Right. So basically what this is telling us is if so we have a ratio of the planetary mass divided by the solar mass, and a ratio of the distance of the sun divided by the distance to the Earth, right? So basically, if this is a large thing, right? If this is 0, approximately, well, not 0, but small, and even if this is not too small, then this is going to be large. So the disturbing force will dominate. So we haven't quantified that, but it's just that's the intuition behind it. Right. So now let's take the alternative approach. Right. Let's consider the disturbance of the motion about the planet due to the sun. Right. If you actually look in Pressing and Conway, they actually when we talk about these disturbance models from the previous lecture, right, they actually give this quantitatively, but so to actually find the changes in orbital elements, and you can find the effect of the moon as well on the motion around the Earth as well, but we're not going to focus on that, right? So again, this is going to be the moon, maybe in our thing. This is the planet. This is the Earth. Okay. And now here's our, again, our standard Keplerian motion, acceleration, / conical terms. And these are our disturbing terms. Now in this case, there's something a little bit different. I mean, the equations look approximately the same, right? So this is the, so what are these things, right? This is the, here's the moon, there's the Earth, right? So this is the, that's that term, right? So that's the standard orbit equation, right? This term, right, is the effect of the sun on the moon, right? So that's this term. Right, so standard stuff, right? Standard orbit of the moon about the sun. But And normally this would be much bigger than this, right? Than this, right? Be much bigger than this. This term is bigger than this term, right? So if there was not this term over here, you would think that the disturbance would always dominate and that the moon would be in the orbit around the sun, right? And in fact, it's almost impossible for this term ever, no matter what the orbit is, right? If you were just in a parking orbit, I believe, this term would still be greater than this term, right? The difference, of course, is that there's this third term, right? And what is this? Well, this is, right, so there's the orbit, right? This is the orbit of the moon with respect to the sun, but we get to subtract off that the orbit of the Earth. Oh, I guess I'm like out of my, like, sorry. Should draw like something there to prevent myself from like writing in there. Okay. So that's the orbit of the moon about the sun, right? And here's the this part is the orbit of the Earth about the sun. Right. So in this case, there is a significant motion. The Earth is in the orbit around the sun, right? So there's this is a non-significant, non-trivial term, and this difference, right? So here, let me just like maybe find a different color to highlight, right? This difference here. Right. The extent to which these two accelerations differ is going to determine the extent of the disturbing force or disturbing acceleration. Right. So if we think about this, right, let's see, get back our yellow. Right. Here's our sun. Here's the Earth, and here's the moon. Right. Right. The acceleration of these two towards the sun is going to be approximately the same. Right? They're being approximately the same. So when you subtract them, right? That term's going to be approximately 0. So if these two bodies are close to each other, right, then these terms over here almost cancel each other out, and so you don't get a big disturbing force, right? So that's the key difference here, right, from the previous, from the orbit about the sun, right? If they're right next to each other, then the two terms approximately cancel out, and you don't get much of a disturbance at all, right? Because the sun is disturbing the Earth's motion in the same way that it's disturbing the moon's motion. Right? So we have to look again at what is the ratio now of, change color. What is the ratio of ... divided by r ... Keplerian. And if we look at that, right, we're going to have something similar. We're going to have ms over mp. Right, so this is a big term, right? And then on the numerator, we'll have a rpv squared term. And on the denominator, well, we get something a little bit different, right? We get this r sv minus r sp. Right? So the question is whether is this greater than what we had on the previous slide, which was RSV over RPV. MP RSV over RPV. Squared. I think that was it. Yep. So, and that is going to determine which sphere of influence we're in. Which Keplerian motion is disturbed more. So again, intuitively, right? When the vehicle is near the planet, again, we got this picture here, right? Vehicle, planet, sun, right? When they're near each other, right? These terms, these vectors, right? RS, V, and RSP, they're going to be approximately equal to each other. Vector-wise. Right. And so if we look at this, right, then the disturbing motions cancel out, right? And so we get this zero term here. Right? So when the objects are next to each other, right, the disturbing force is not significant, right? The Keplerian motion looks pretty Keplerian. Right? So now we define rigorously, or I don't know, formally, our sphere of influence model, which is basically what I was saying. When the disturbance, the ratio of the disturbing accelerations over the Keplerian acceleration is greater than right? When that ratio is greater, then you're out of the sphere of influence, right? So if the disturbance is, that disturbance is small relative to the general overall acceleration, then you're in the sphere of influence of that body. Right? So the question, of course, becomes how to determine those numbers, and it's fairly complicated. And you know, there are cases where the sphere of influence is not spherical, right? So the best case I can think of, right, for example, is the Earth Moon, right? So here's the Earth, here's the Moon, and here's the sphere of influence of the Earth. And embedded within that, right, is the sphere of influence of the moon, right? And actually, it would be extending a little bit non-spherically that way. Right. So, right. So technically, the sphere of influence of a body does not have to be spherical. Right? But we generally make that approximation. And most of the time, if we're not thinking about the moon, because the moon's a little bit more complicated, if we're thinking about the sun and the earth, then the spheres of influence of the planets are relatively spherical. Right? So here we have a rough and ready formulation or approximation for the sphere of influence of a planet. Obviously, if you're not in the sphere of influence of a planet, you're in the sphere of influence of the sun. So the criterion is that your distance to the planet right, should be less than the mass of the planet divided by the mass of the sun to the power 2/5 divided by the distance to the planet. Right? Distance of the planet from sun. Right. So distance of vehicle, right? Yeah. The distance of the vehicle to the sun, to the planet, has to be less than this number. Right. In order to be in orbit around the planet, as opposed to orbit around the sun, which is the converse case. When you're not in orbit of the planet, you're in orbit of the sun. So this is just a a pretty simple derivation of that little rule, just to give you an idea of where it comes from, right? So our criterion is that we want the disturbance of the planet to be less than the disturbance to the sun, and so for that to happen, well, we just plug in our formulae for the disturbances, right? And we get this criterion. So we just multiply through these. These probably look familiar, and then we so these are the disturbing forces, and then we have the sun thing here, right? So that's the criterion. Now we make this approximation here, right? So that the so we make an approximation here that RSV is approximately equal to RSP. So that the distance, the distance from the sun to the vehicle is approximately equal to the distance, like magnitude-wise, of the planet. Right? And that's a pretty good approximation, right? So remember how small those little sphere of influence lines were, right? So this is a pretty good approximation. Where's my sun? I'll draw a little sun there, right? And draw vehicle, and draw another vehicle. Right. So we do that approximation, and so this is equal to that, right, on the denominator. So we replace that with SV, and so that those common denominators plug down to right there. So we got this vector difference on the top. We got PV still down here, RPV right here. And so we simplify this expression by moving this term up here, this term down here, and what else are we doing? Oh yes, and we move this term up here. Oops. Right, make it to the power fifth. And this term, it's an inverse of an inverse, and so that goes over there. So it plops up to the top, and then we bring it back down to the bottom, and that gets up to the power fifth. So now our criterion then is this one. Now we make the approximation here that, again, this vector difference, because remember what this vector difference is. Well, it's not actually an approximation, it's actually correct. The vector, right, RSV, RPV, now we're in vectors, not magnitudes. And so you take that difference, and that'll give you the vector from the planet to the vehicle. Right? So that's actually not approximate, that's equal to 1. And so we just we divide then through solve for the RPV, right? We want to find the distance to the planet under which this condition holds. Applies that. So we just solve for RPV. Divide by, take the fifth root of this term. Of course, you take the fifth root of this term is just this itself. And this is to the power squared, so 2 divided by 5. Right? So that's our rough and ready rule for when you're in the sphere of influence of a planet. And of course, if you're not in the sphere of influence of a planet, you're in the sphere of influence of the sun. Right. So what are these numbers? Just for intuition. Earth, right? We're out to 145 Earth radii, which is the magnitude of 924,000 kilometers. Venus, 617,000 kilometers. Mars, 574,000 kilometers. Now, remember, Mars is much lighter than the Earth, and that's why it has a smaller sphere of influence than both the Venus and Sun. Actually, as you get closer to the Sun, of course, the sphere of influence diminishes in general. So that's why when you get farther out, right, your sphere of influence boosts up, right? Although the mass of the planet also plays a factor there. So both those. And then Mercury is a relatively small planet, only 45 Mercury radii, or 113,000 kilometers. So you have to be pretty close to Mercury to actually be in orbit around Mercury. And these are just applications of the formula. Except for this one, of course, which is a little bit different. Right? That's the moon. Moon, sphere of influence, of course, not very big at all. 66,000 kilometers for the sphere of influence of the moon. But it's a sizable chunk sitting inside the sphere of influence of the Earth. Right? Notice that the distance, right, to the our Earth to the moon is only, I believe, 850,000 kilometers. Right, so it's less than 924,000 kilometers, right, which is that number. So the sphere of influence of the Earth, right, if you add 850 to, 66,000, right, that's still less than, right, plus 66 is still less than 924, I believe. And so sphere of influence of the moon is inside entirely the sphere of influence of the Earth. Interesting. So if you pass by the moon on the way to Mars, you'll leave the sphere of influence of the Earth, enter the sphere of influence of the moon, leave the sphere of influence of the moon, enter the sphere of influence of the Earth, and leave the sphere of influence of the Earth, and enter the sphere of influence of the Sun. So you don't really need to pass by the moon on the way onto Mars or wherever, but just FYI. Right? So some of that information there. Well, didn't mean to cross that out. Information inside. Yeah. Okay, so that covers pretty much our sphere of influence, which is a little bit technical. So now we're going to be talking about something which is relatively non-technical in a minute. First of all, though, I'll just do a really quick example. So I messed up actually on the previous slide. So the distance to the Earth Moon is not 850,000, it's 350,000. So my bad. I'm not sure how I messed that up. So clearly 850 plus 66 is less than 924. So my bad. Yes. So we're designing a lunar lander mission, right? Just an example, right? One of the ways you do that, right, is you put yourself in a parking orbit. There's your parking orbit. Then when the timing and the inclination are right, and we'll talk about that in a second, you go on a transfer with an apogee, right? If you didn't get to the moon, our apogee of, what did I say? So the sphere of influence of the moon extends down to 318,000 kilometers. When you get to the sphere of influence of the moon, right, you just do a little delta V here to put yourself in a circular orbit around the moon. Right, you do inject into the, you get close to the moon and then do an injection here, retrograde burn. You inject into the moon. You descend to the surface. You come back up, and at some point here, you do a posigrade burn to leave the sphere of influence of the moon and re-enter the sphere of influence of the Earth, and then you do a delta V burn here to re-enter the Earth. Now, the moon is a bit of a tricky bit because so the moon is not, so the moon orbits the Earth. I think we can safely say that moon orbits the Earth, but its orbit is a bit odd, and it suffers from some perturbations. The main perturbation to the lunar orbit is due to the sun. So it suffers from some perturbations. It's inclined. It's not in the ecliptic, but it's close to the ecliptic. So it's not in the ecliptic. It's not in the equatorial plane. And so there's like this inclination of the moon's orbit, which actually changes over time. And so at some point, you're going to need to transition to the lunar plane. It's possible to do. It depends on what year it is, right? So, you know, when you get to the lunar orbital plane. So let's talk about the lunar orbital plane in just a second. Depends on the time of year. So what is the orbital plane? What is that plane change maneuver? Why is it required? And that's because remember this dichotomy, is the moon orbiting the sun or is the moon orbiting the Earth? Well, the Earth disturbs the motion around the sun, and the sun disturbs the motion of the Earth. So it's actually sort of an average. You sort of you split the difference in a weird way. So remember that the sun is in the ecliptic, right? The sun is in the ecliptic, right? And so normally the orbital elements, you have an inclination. Inclination is fixed in Keplerian orbits. Inclination is fixed. Now, if the moon were orbiting the Earth, its inclination would be fixed with respect to the Earth. I put a little question mark because it's not. Oops. Undo that. Too bright. Right? It's not. Right? So, okay, here's the geometry, right? So here's the Earth, right? You have your equatorial plane here, right? Equatorial plane. You have your ecliptic plane. Here's the first point of Aries. Right? There's the North Pole, right? And here's the lunar orbit, right? So the lunar orbit is not in the ecliptic. It's not in the ecliptic, but for some strange reason, it's fixed with respect to the ecliptic. It's fixed. It rotates a little bit, precesses a little bit. It's fixed with respect to the ecliptic and not with respect to the equatorial plane. But so this is not true. for the moon. So the moon is this weird case where almost all the orbital elements of the moon are fixed, except one, which is the inclination, which is fixed to the sun, to the ecliptic plane. So remember, the ecliptic plane is the orbital plane around the sun. So the inclination of the moon's orbit is fixed with respect to the ecliptic, and it's fixed at an inclination of 5.15 degrees or so. Right? What of course means that actually the inclination to the equator, the inclination of the moon's orbit with respect to the Earth, varies with time. Right? And its period is 18 years, right? So it goes up above, right, the ecliptic, and it comes back down below the ecliptic, and it does so every 18 years. That's because it's precessing about this this ecliptic. So it's like a top. It precesses every 18 years. Right. So some years, consequently, in certain years, the moon appears higher in the horizon for the northern hemisphere people or the southern hemisphere people, and sometimes it's lower than the horizon, right? So if we're on Earth, right, and we're looking up at the sky, right, sometimes the moon gets up there, and sometimes the moon stays down here. And that's plus or minus, or that's a delta of 10 or 11.6. Oops, I guess that's right. You can't see that. Right? So we'll do the southern hemisphere people. Right. So the position of the moon above the local horizon varies by delta I of, or delta declination of 11.6 degrees. Okay, you still can't see that entirely, can you? Sorry about that. Right. So here's the right ascension actually also precesses with also a period of 18 years for the same reason, right? That it's precessing with respect to the ecliptic, and that means it's also precessing with respect to the so it precesses with respect to the ecliptic. So this also rotating in the ecliptic, which means, of course, that it also rotates in the equatorial plane. So these right ascension and inclination fixed in the ecliptic, so in the solar orbit, but not in the Earth orbit, which is a bit weird. Right. So just keep that in mind when you're going to the moon, that actually there's some times that are better than others, right? Specifically if you're launching here, right, at Cape Kennedy, for example, that's 23 degrees. I think, no, wait, it was 28 degrees, sorry. 28 degrees inclination. So remember, if you launch from Kennedy, you can't launch directly into an inclination of greater than 28 degrees. And if you're high in the Saros cycle, sometimes the inclination of the moon will be 23 plus 5, 23 plus 5, well, actually it is 28. Okay. So actually, pretty much all the time you can get to the moon. But, if you were launching from Russia, for example, right, at a higher latitude, then you want to pay attention to the Saros cycle. Okay. So again, this inclination of the Earth's orbit with respect to the Earth changes from a minimum of I don't know, was it 18 degrees or something like that, to a maximum of 28 degrees or maybe 29 degrees or something like that. It doesn't look like a degrees, does it? Sorry about that. All right, so that's pretty much what I wanted to show you. I got some this is the orbital plane of the moon as it processes around, again being pulled by the sun with respect to the ecliptic plane. This is in the Earth-centered inertial coordinate system. And then again, here's the orbital plane processing about the Earth-centered inertial coordinate system, the Saros cycle. I think these are from Wikipedia. You can see the right ascension and the inclination changes going on there. And finally, I'll just give a this little GIF here for a mission to the moon. So this is a continuous thrust cargo mission, right? So you're getting higher and higher into Earth orbit. At some point, however, you transition to the sphere of influence of the moon, and then your orbit looks non-Keplerian from an Earth-centered perspective. Right. So here we're making actually a couple changes here to our orbital elements. Let's see, and then we meet. There's the moon. We get into the sphere of influence of the moon. Actually, these are delta V's. These green changes, and then we look distinctly non-Keplerian from the Earth's perspective. A little spirally action going on there. Land on the moon, and using our continuous thrust maneuvers, we eventually decrease our energy and land on the moon. So what did they have to say about this? Total delta V going on here. Power 200 kilowatts. Remember from our rocketry, 200 kilowatts is for one of those electric thrusts. ISP of 500 seconds, 5,000 seconds. Sorry. So what would that be? That would be an ion thruster. They can get up to about 5,000 ISPs. Anyway, so at this point I will pause and restart in a minute to allow you to take a break and digest this bit of information. We'll start again in a minute with the interplanetary mission planning part.